I left you with 3 questions. Let me make some comments on those and then tell you about a fantastic picture called the Mandelbrot set. Okay, so my questions were, what are those 3 complex numbers? So how to do that first one? Okay, Euler said that this is the same as the cosine of pi over 2 plus I times the sine of pi over 2. And those are things that we know. That's 90 degrees. The cosine of 90 degrees is 0. And the sine of 90 degrees is 1. So I have I. The answer to that question was an amazing number. E to the I pi over 2 equals I. What about e to the I pi? Okay, if we follow Euler again, that's cosine of pi plus I sine of pi. 180 degrees, the cosine has dropped to minus 1. The sine of 180 degrees is 0. And I get minus 1. A lot of people think this is a wonderful formula. E to the I pi is minus 1. If I put the number I pi into that infinite series and add it up, you won't see it happen, but somehow at the end, the whole thing adds to minus 1. And now this was a crazy one for teachers, for professors. What could I to the I be? What sense can I make of it? Let me suggest a way to do it. That I is, according to our first formula, e to the I pi over 2. So that I is e to the I pi over 2. Thank you, Euler. To the power I. Now I've got something I can work with. Do you remember what the rule is for exponents when you take a power? If you took x cubed to the 4th power, that would be 3x's times 3x's times 3x's times 3x's, 12x's, x to the 12th. You multiply the 3 and the 4. Here I multiply those guys. So it's e to the I times I pi over 2, which is minus pi over 2. Look at that. I to the I has come out to be some real number. And I don't actually know what the digits are. You'll find them. Anyway, that's the amazing answer to I to the I. Now for the Mandelbrot set. Can I first ask a question to lead into the Mandelbrot set? Remember the complex plane. Remember the unit circle, the things of size 1. Suppose I start with a complex number there. Start with z. Look at z, z squared, z cubed. Forever. What do I get in the limit? So I take that number z. The point about that number z is that it's inside the unit circle. What does that mean? It means r is less than 1 in here. Then what about z squared? Z squared, the magnitude of z squared is r squared. The magnitude of z cubed is r cubed. And with r less than 1, those numbers are getting small. My conclusion here is that that goes to 0. Suppose I take instead a number out here. That'll be my second number. Out there, r is bigger than 1. Now I do z, z squared, z cubed, so on. What's happening here? When I multiply that number by itself, the r's will multiply to give r squared. The angles will add, so it'll be a number down here. It'll be about there. That'll be z squared. Z cubed will be further out. This will go to infinity. Okay. And points on the circle. Now let me take a point on the circle. What happens to those? If that's this is r equal 1 on the circle. The square of that is on the circle again, at twice the angle. The cube is 3 times the angle, 4 times the angle. So I'm running around the circle. I'm running around the circle, or jumping around the circle, when I take powers of that one. All right, now for Mandelbrot. Mandelbrot had a fantastic idea. This Mandelbrot set is going to be a part of the complex plane. It won't look like a circle. It has a very, very strange shape, which you'll have to see with a blown-up picture. What I want to do is the math part to tell you where did that Mandelbrot set come from. So you remember with what we did first, I took a number, I squared it, square that, square that, square that. Mandelbrot had the idea, let the n plus first one be the square of the nth one. So if he stopped there, we're just taking powers of the original z0. But you're going to add in a constant, say w. That'll be another complex number. Okay. So, and I have to start this thing with z0 at w. Okay. So here's the question that Mandelbrot asked himself. If w is some complex number, anything in the complex plane, I start z0 at that number w, then what is z1? z1, I take one step, is z0 squared, that's w squared, plus the w. Okay? That's some other complex number, maybe bigger, maybe smaller. z2 will be that number squared, w squared plus w, all squared, plus one more w from there, right? I just keep going, in theory. And I ask the question, do these numbers blow up or not? If they don't blow up, I put w, that complex number, in the Mandelbrot set. I put w in the Mandelbrot set. So let me do an example. Suppose w is a pretty small number. Then I start small. That doesn't add much. That doesn't add much. If w is small, it's going to be in the Mandelbrot set. All right, so let me put a w. There's a small w. If w is sort of big, it will be outside the Mandelbrot set. And so the Mandelbrot set is some crazy set with little pieces on, little pieces on, little pieces on, little pieces on those pieces, which contains all the w's, so that if I start with w, go to w squared plus w, go to that squared plus another w, go to that squared plus another w, and keep going, if w is in this set, I don't blow up. So w, the Mandelbrot set is all the w's that stay bounded when you do this little bit crazy iteration on them. Okay, you'll have to see a picture of that. That comes next. Thank you.